Hi everyone, today I'm going to show you how to make pure concentrated sulfuric acid from cheap household products by electrolysis of copper sulfate. There are many reasons for wanting to make sulfuric acid at home. For example, in my case, I mainly use it in order to make nitric acid, which I can use for pyrotechnics. So, if you look at my video on how to make nitric acid, you will see that I start from sulfuric acid that comes from a specific brand of clog remover. The problem is that this brand seems to have vanished from the market, and the other brands only propose sulfuric acid that is purposely polluted with a bunch of other chemicals. It is still possible to buy pure sulfuric acid on eBay, but it is relatively expensive. So the solution for me is to make it myself. By the way, you will find the link to my video on how to make nitric acid in the description of the present video. So what you are going to need is some distilled water, 98 cents at Walmart for 1 gallon, and some copper sulfate. Mine comes from the Home Depot as rootkill from the Z brand, and it cost about $15 for 2 pounds. If you look at the constituent, it says that it has 99% of copper sulfate, pentahydrate, and 1% of other ingredients. So these are impurities, which are fine if you only want to make diluted sulfuric acid, but in my case, I want to make sulfuric acid concentrated to 98%. So we have to get rid of these impurities. And that's easy. I'm not showing it in this video, but all you have to do is to dissolve the copper sulfate in boiling water and let it recrystallize by letting the water evaporate. The impurities will fall at the bottom of the container and the top of the crystals will be pure. So here my bottle already contains the purified crystals. Alternatively, you can buy pure copper sulfate on eBay or Amazon, and it's not too expensive. You will also need a voltage supply, and I strongly recommend using one where you can adjust the voltage. Now, don't worry if you don't have this. You will also get good results if you use a fixed voltage supply like 6 volt or 12 volts. Now, to do an electrolysis, you need a cathode and an anode. Initially, the cathode could be made of any conducting material, but as some sulfuric acid will be produced, we want this cathode to be inert when in contact with the acid. So here we can use a copper electrode, since sulfuric acid won't be able to dissolve it. Mine simply comes from plumbing scraps. For the anode, it is slightly less simple as most conducting material would be oxidized. They would decompose and pollute the final product. Most people use carbon anodes. It is fine if you don't care about the purity of the acid. Carbon anodes get corroded, and by doing so, they turn the acid black. You can filter part of it at the end, but you won't be able to remove it all. Now, if like me you want a very clean acid, you have two options. The expensive solution is to get a platinum electrode, which is totally inert. The solution I propose is cheap and even virtually free, and consists of using a lead dioxide electrode that I made. How did I make it? I got some lead from plumbing scrap that I melted into a mold made of plaster. It is very easy to melt lead with a torch, so you can do it yourself and give it the shape that you want. So you can easily make a lead electrode, but I said that mine is a lead dioxide electrode. How did I make it then? Well, don't worry about this right now. Just use a lead electrode for the time being, and I will explain in a moment. Now, take a jar that is large enough to contain 600 milliliters of distilled water. So, let us measure this. It doesn't have to be very precise. And we are going to measure 45 grams of copper sulfate, purified copper sulfate. I guess I should turn this on first. All right. And once again, this doesn't have to be very precise. Okay, 45.70. That's perfectly fine. And we're going to dissolve as much as we can. And here I'm using a glass rod. You don't want to use a metal rod because copper sulfate in solution can react with it, and it will definitely react when we will have produced some sulfuric acid. So dissolve as much as you can. It's okay if there are some that remains at the bottom. As we will do the electrolysis, some of the copper sulfate will turn into sulfuric acid, and the solution will be able to dissolve the remaining copper sulfate. Okay, you can leave the rod in it. Alright, so now we are going to put the copper electrode into the jar and connect it to the negative. Okay. And I put my lead dioxide electrode. You will put your lead electrode. Okay, so first let me connect it to the positive, and then I'll put it like this. Yeah, well, let me attach it. I don't want the cable to be in the solution, otherwise it will get corroded as the electrolysis will be going on. Okay, it's not easy to do this in front of the camera. All right, that's good enough. Okay, and now, well, let's turn on the power supply. Let me put DC current, and I'm going to increase the voltage until I get about 500 milliamps. All right. Okay, so right now I have 9.5 volts. Now I need to make a zoom on what is going on here. Well, first It's hard to see, 9.5 volt, and I have 500 milliamps. Okay, now you can see that on my lead dioxide electrode, you see those bubbles. Let me try to focus this. Yeah, you see those bubbles, right? So that's oxygen that comes from the breaking of water molecules into oxygen and hydrogen. No bubbles form at the cathode. Instead, some copper is plating the electrode, which becomes bigger. Hydrogen atoms coming from the water molecules are broken at the anode, and they replace this copper, turning the copper sulfate into sulfuric acid. Now, as the electrolysis is progressing, the current will increase. That's because the sulfuric acid that is produced gives the solution a better conductivity than the copper sulfate. So eventually, you may want to reduce the voltage because a current too large might be destructive to both the anode and the power supply. My power supply doesn't like the current to be greater than 1.15 amps, so I will progressively decrease the voltage. Now, as the electrolysis is progressing, you will see that your lead electrode is getting oxidized and turning black, leaving some residue in the mixture. That is perfectly fine, first because the residue will be easy to totally filter out, and second because this oxidation will stop when the anode will be totally black. When this happens, you have your lead dioxide electrode, and for your next batch, you should no longer observe any residue. So all we have to do at this point is to wait, but how long? Let us make a simple calculation. So we have our jar with the lead dioxide and copper electrodes. This jar is filled with water, and although it is distilled water, some of the molecules split into ions H+ and OH- due to thermal energy. When we add the copper sulfate crystals, they split into copper ions and sulfate ions. Now, the cathode supplies electrons, so only reductions can occur, and we have two possible mechanisms. The first one corresponds to two H+ ions that each take one electron to form a hydrogen diatomic molecule that bubbles out of the solution. This mechanism is associated to a reduction potential that is defined to be 0 volt. The other possible mechanism is that a copper ion takes two electrons to form a copper atom. This second mechanism has a reduction potential of 0.34 volt. Since the reduction potential quantifies the ease of a reduction reaction, the one that takes place is the one that has the greatest potential. Thus, it is the copper ion that is reduced and sticks to the cathode, which becomes bigger. Note that as the solution will eventually run out of copper, the other reaction will take place and hydrogen bubbles will appear at the cathode. At the anode, electrons are taken from the solution, so only oxidations can occur. Again, two mechanisms are possible. For the first one, electrons are taken from two water molecules, which splits into four H+ ions and one oxygen diatomic molecule that bubbles out of the solution. This mechanism has a reduction potential of 1.23 volt. For the second mechanism, two sulfate ions SO4 2- each lose one electron and associate to form one persulfate ion S2O8 2-. This mechanism has a reduction potential of 2.01 volt. Since only oxidation can occur at the anode, the mechanism that wins is the one that has the least potential for reduction. As a result, two water molecules split into four H+ ions and one oxygen diatomic molecule that bubbles out of the solution. With these considerations, the global reaction equation is easy to write. Initially, we have sulfate compounds in the solution, and they remain in the solution at the end. Each of these sulfate compounds are initially associated to a copper atom, which at the end sticks to the cathode. Each of these sulfate compounds end up being associated to two hydrogen atoms that can come only from a water molecule that splits, thus leaving a half diatomic oxygen molecule. We obtain our global reaction equation. Now we used for our initial mixture 600 milliliters of water and 45 grams of copper sulfate pentahydrate. It is important at this point to mention that pentahydrate means that each copper sulfate compound is attached to 5 water molecules, and that's what gives it its beautiful blue color, as opposed to its anhydrous form, which is white. Taking into account these 5 water molecules, we can calculate the molar mass of the compound to be 249.7 grams per mole. The number of moles of copper sulfate pentahydrate is equal to the mass divided by its molar mass, which gives 0.18 mole. The number of moles of CuSO4 is the same, since there is exactly 1 CuSO4 for each copper sulfate pentahydrate compound. According to our global reaction equation, each copper sulfate compound turns into a sulfuric acid compound. Thus, we must end up with 0.18 mole of sulfuric acid. Since the molarity is the number of moles per liter, we can predict the molarity of our sulfuric acid at the end of the electrolysis to be 0.3 moles per liter. We can now answer an important question. How long will the electrolysis take? We better know in advance if it will be done in a matter of hours or days, or if a few centuries will be necessary for it to complete. So the calculation is pretty simple. For each copper ion reduced by the cathode, we need 2 electrons. Thus, we need a total of 0.36 mole of electrons. The corresponding charge is obtained by multiplying this number by Avogadro's number and by the charge of 1 electron. We get a charge of 17,300 coulombs. Now, 1 coulomb is also 1 ampere second, that's the definition of the ampere, and by dividing by 3,600, we get 4.81 ampere hour. This means that with a constant current of 1 amp, the electrolysis should take nearly 5 hours. Since I'm starting with a current of 500 milliamps, and assuming that I would maintain it like this during the entire process, the electrolysis should take about 10 hours. Now, this is just an order of magnitude. I won't be staying in front of the power supply for 10 hours trying to adjust the voltage to maintain 500 milliamps, so the current will actually be greater. Will that make the electrolysis faster then? No, because we haven't taken into account the fact that the cathode will eventually be depleted in copper ions because the solution is not constantly stirred. So the cathode will reduce a lot of hydrogen ions too, at the expense of the copper. This won't pollute the solution since the hydrogen will bubble out, but it will slow down the whole process. The point is that we know that the time needed is a matter of hours that can be doubled or even tripled, so maybe a day and a few hours, but definitely not a year or a century. And that's good to know because we know that the electrolysis is doable. So we will obtain 600 milliliters of 0.3 mole per liter sulfuric acid. That's very dilute. However, it is easy to concentrate it simply by boiling off the water. In principle, by doing so, it is possible to reach a concentration of 98%, where the acid forms an azeotrope with water at 337 degrees Celsius. If you look up online, The molarity of 98% concentrated sulfuric acid is 18 mol per liter. That's 60 times greater, which means that our 600 milliliters of dilute acid will be reduced to 10 milliliters once the highest concentration is achieved. It has been 10 minutes that I started the electrolysis, and now see how the current increased. I didn't change the voltage, but now the current is 710 milliamps. So let me reduce a little bit the voltage, because I want to leave this for hours, and I want to make sure that the current won't get bigger than 1 amp, otherwise my power supply will blow up. Okay, I'll leave it like this for a while. And as you can see, there is no residue falling from the anode because it is no longer getting oxidized. Now you have to be very gentle with the electrode, because the black coating doesn't stick very well to it. So if you give it a shock, the plating will fall as a residue, but it's okay. In all cases, the residue doesn't dissolve in the solution, so you can easily filter it out. But still, it's better if you don't get this residue at all to start with. Okay, it has been 8 hours, and now you see that I had to decrease the voltage down to 4 volt, and yet I have 720 milliamps. And here you can see that the solution has cleared up. The top is clearer than the bottom. So well, that means that the solution, of course, is depleted in copper sulfate. So I'm going to stir the solution in order to dissolve more of what is in the bottom. And well, as you see, this has the effect of increasing the current. So I'm going to decrease the voltage a little bit. Alright. Now you can also see that the copper electrode has become bigger. There's some spongy copper that was that plated it. Now this is very soft. There are some pieces that may fall in the mixture if you touch it, and that's fine, because once again, this is copper that won't dissolve in the solution, so they are very easy to filter out. Okay. Now, why is the cathode plated with spongy copper instead of a very fine and smooth layer? Well, that's because the current is actually way too big for doing a nice copper plating. But here we don't bother about copper plating the cathode. We only want the electrolysis to go on, so it's perfectly fine to use such a current. We could even use a larger current, not too large, because otherwise this would destroy the anode, unless I would use a bigger anode, which I don't have. Okay, so alright, let me try to dissolve a little bit more of this copper. Alright, and I'll do the same thing in a few hours. Alright, so it has been about 12 hours now, and first well, you can see the voltage is 3.9 volts for 840 milliamps. So the conductivity increased, and now all the remaining copper sulfate has been dissolved. Now you can see that there is some residue that comes from the cathode, the copper that is not sticking to it, so it falls in the jar. And also there's a little bit of the coating on my lead electrode that fell, but it's perfectly fine. Once again, this doesn't dissolve at all in the solution, so we will be able to filter this out and obtain a perfectly clear solution. All right. Also, the solution now is being depleted, so it started to clear out, and well, we have to wait a few more hours for that, for the electrolysis to be complete. Now, as we have seen, the molarity of the initial copper sulfate solution was 0.3, and it can be calculated, but it's a little bit complicated. So if you simply look online, you will find that the pH of this of 0.3 molar copper sulfate solution is about 4.6. So now here I have some pH paper, and let us see if the solution has gained some acidity. So yes, definitely it's being acidic. If we want to compare the color, you see that the pH is already close to 1, so it's definitely acidic. Unfortunately, my paper cannot go below 1, but when the acid will be concentrated, the pH should be around 0.1, I think. But well, we won't be able to measure this. Okay, but the fact that the paper turned red is a really good indication that we are indeed producing some acid. So now the solution is completely clear, and well, it took about 24 hours, but just to make sure that there is no copper sulfate left, I left it for 12 hours more, so that's a total of 36 hours. Now you can see that we still have those bubbles at the anode, so that's oxygen. But now that there is no more copper at the cathode, you can see that it also bubbles hydrogen. All right. So now let us filter this out. Okay, so we can turn this off. Be very gentle with the carbon dioxide electrode so that it doesn't lose its coating. So our copper electrode got much bigger, but it's very spongy. It doesn't stick. The copper doesn't stick to the cathode because the current was too large for doing a nice, very smooth layer that could stick on it. Okay, if you want to copper plate metal pieces, you have to use a very small current so that the copper atoms have time to spread all over the piece that you want to plate. And if you do this, then it will stick very well. Okay, but that's not the point of this experiment. So let us remove this. Now I'm going to filter out the copper that fell at the bottom of the jar. And well, here I'm going to use a simple paper coffee filter, and that may introduce a little bit of pollution because the sulfuric acid will actually react with the paper. But since the concentration is very low, we have a very weak, a very diluted acid. Remember, we calculated its molarity to be 0.3 mole per liter. So hopefully it won't have time to react too much with the paper and won't introduce too much pollution. However, when we will concentrate the acid, this pollution, the concentration of this pollution will also increase. So, well, we will see what we will get when it will be concentrated. Right. So you see that it's pretty clean. And let us make a quick test. Look, we made some diluted sulfuric acid, perfectly clean. Alright, so now we need to concentrate it. Alright, so we are now ready to boil off the water in order to concentrate the acid. Definitely you should do this outside or under a fume hood. I don't have a fume hood, so I'm doing it here. At the beginning, it's mostly water that will boil off, but as the concentration of the acid will increase, the boiling temperature is going to increase too. And theoretically, we could reach a concentration of 98% at a temperature of 337 degrees Celsius. I won't go that high because as the concentration increases, the acid will suddenly start to boil some fumes that are highly toxic and corrosive. So as soon as I will see those fumes, I will stop boiling the acid, and then we will see the concentration that we get. Now, I suggest using some goggles when doing this because, well, although it's Pyrex, we always have to take into consideration the possibility for the glassware to break. And, well, of course, it's dangerous not only because it's acid, but it's dangerous because it will be really hot, and also because the heat capacity of sulfuric acid is greater than that of water, which makes it even more dangerous if it ends up on your skin. So at least protect your eyes. Okay, now I suggest putting some sort of insulation around the flask in order to prevent the wind from cooling off the bottle, so it will be easier to reach the boiling temperature like this. Alright, so now all we have to do is to wait, and once again when I will see the fumes, the white fumes, then I will stop the heating. And also we will have to let it cool off on its own. We shouldn't try to make it make it cool faster by blowing on it or putting it on some cold objects. Otherwise, because of the thermal difference in temperature, that could break the glassware. Alright, so it has been 30 minutes, and now we can see that we have some bubbles, and here this is mostly water vapor. So we have to wait. It is now about to reach a large concentration. There is not much left in the flask. Let me wait just a few more minutes. Finally, here is our concentrated sulfuric acid. There is not much left as we expected. And there's also a little bit of white residue at the bottom, so I don't know if this residue comes from when I filtered the diluted acid with the coffee filter, and the acid ate a little bit of the filter, or if it's due to those white fumes that we saw when I was boiling the water off. Those white fumes probably produce some residue, but anyway, if you let it stand for a while, those residues, they go at the bottom, so we can decant the acid. So I'm gonna do this right now. First, I want to measure the mass of my measuring cylinder so that we can make a rough estimate of the mass density. of the acid and relate it to its concentration. All right, so 19.38 grams. Okay, so remember this number, and now I'm gonna pour this in this glass dish because I don't want, since the acid is very concentrated, I don't want it to ruin my table. And let me try to adjust the camera. Sorry, that's not a very professional video. Problem is that I cannot filter out those residue. I don't have a filter that can withstand the strength of the acid. Alright, well, I'm gonna leave some in the flasks in order to avoid putting too much residue. So let me try. Okay, so well, the resulting acid is not too dirty, and we have 8 milliliters. There's still a little bit in the flask with the residues, and also we lost some each time I transfer the acid from one container to another. There's always some that remains on the walls of the flasks. So, but I mean, 8 milliliters compared to the 10 to the predicted compared to the predicted 10 milliliters, I think that's not bad. Okay, so okay, 8 milliliters. Let us measure the mass. And all right, 33.35 grams. So okay, I don't remember what was the previous value, so I have to review the video. I'll come back to you and we'll make the calculations in order to calculate the mass density. In the meantime, let us prove that what we have is really concentrated sulfuric acid. Well, first, we will see from the mass density that it's much higher than water. That is higher than 1 gram per milliliter. Also, you can see that the product is very thick. It's viscous, and this is an indication that what we have is concentrated sulfuric acid. Okay, but let's do another test. I'm gonna pour some on a piece of napkin. And let us see what happens to it. Yep, nice. See how fast it dissolves? So I hope that you are convinced that what we have is really concentrated sulfuric acid. Okay, I'll get back to you with the calculation in order to determine the mass density. So the mass of the empty cylinder was 19.38 grams, and the mass of the cylinder with 8 milliliters of sulfuric acid was 33.35 grams. So that means that the mass of sulfuric acid is 13.97. And well, that means that we only have to divide by 8 in order to obtain the density in gram per mil. So that's 1.75. And currently the temperature is 25 degrees Celsius. So if you look online, you can see that you will find some tables that indicates that a mass density of 1.75 grams per mil corresponds to a concentration of 83%. So that's relatively highly concentrated, not as much as I hoped I would have. Actually, when I did my last batch, which unfortunately I didn't get on video, I was able to achieve 92% concentration. In principle, we can still increase the concentration by boiling of more water. We just need to keep in mind that when we concentrate the acid, we also concentrate the impurities. So we need to get a mean of removing those impurities first. Okay, but I would say that this is definitely a success. Now, of course, the yield is very small, and all we have to do is to scale up this thing. So instead of using a jar, next time I will do this into a large bucket, and I will use sheets of copper and lead instead of rods. But the process will be exactly the same, and this way we should be able to obtain a decent amount of sulfuric acid. Alright, thanks for watching. Please register to my channel, and don't hesitate to comment.